anyways, let's continue further. All right, let's take a look at parallel planes. So two planes are parallel if their normal vectors are parallel. That is, it's a normal vector like this, and it's then you have another one like this as well, pointing in the same direction. Then you have the same. Then you have parallel planes. So, for instance, the planes x plus 2y minus 3z equals 4, and 2x plus 4y minus 6z equals 3 are parallel because their normal vectors, right here is 1, 2, negative 3, so 1, 2, negative 3, and this n2 is, this is going to be 2, 4, negative 6. Yeah, so because that's their normal vectors, and n2 equals to 2 and 1. You can see these are just multiples of it, so all you're doing, these are parallel because you're just scaling these up by 2. You're just multiplying this every component by 2. Like that, so it's exactly parallel. So this one, in this case, you have one vector that's pointing this way, and then the other one is the same but double. So this is going to be 2x. So it's parallel. So then you're gonna have parallel planes, and this term right here, the 3 and 4, that just shows it. Yeah, that just shifts it in space, but it's gonna be still parallel. All right. So if two planes are not parallel, then they intersect in a straight line, and the angles between the two planes is defined as the acute angle between their normal vectors. Yes, and as shown in the figure below. So yes, if you have any non-parallel planes, they're always going to intersect, because you're going to infinity, and yeah, just geometrically speaking, it will intersect. So let's draw two planes. So let's say you had a plane like this here. I'll make this a straight line. Like this, and then you had another one. I mean, this is the same plane. All right. So there's one plane. All right. So let's say that's one plane. Now there's another one like this, and there's that angle to it. And I'm going to draw this angle as theta. So this angle, and I'm going to go as dashed lines across dot dot dot, and this dot 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 all the way across here, like that. There's the line there. Alright, so let's say that at the bottom here of this plane is we'll call that plane 1. That's gonna have a, like this. Let's put a dashed line, going dashed up, like this, dash, 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 and then it goes through this point all the way across, all the way on top here. This is gonna be your n1 vector, like that. So now, because yeah, this one here is this is angles is theta like that. The next one is going to be, and this is from the bottom plane. The next one we're going to have, let's say it's going to be on this plane, on the top plane, and that's going to be, well, yeah, this is going to be pointing out like this. Actually, instead of going all the way there, let's make it right next to it. Yeah, just made it right next to it, and I'm going to do is I'm going to draw a line like this. This is going to be perpendicular to the top plane, and now we have an angle here. This angle is going to be also theta, and you can see this is a theta. This is exactly the same because you're turning it both by the exact same. For example, if you had it, if you had both of these flat, the angle is going to be 0. Theta is equal 0, and then the difference between these are also going to be 0. They're pointing the exact same direction, so then the theta equals 0 on the top, and then as you rotate either or. Yeah, so if you had, let's say you had here, and you had it flat, so you initially had 0, theta equals 0, and then you shift it. You can shift by exactly the same amount. Theta, theta. So that's all you're doing is turning it. So yeah, so the angle is going to be the difference between these. And this is going to be our n2. Alright, so now let's continue further and take a look at an example on this. So example 7, so part A states, find the angle between the planes x plus y plus z equals 1 and x minus 2y plus 3z equals 1. And then part B states, find symmetric equations for the line of intersection L of these two planes. Now we get an interesting little nugget here. So solution to 7a. So the normal vectors of these planes are, and again, the normal vectors is going to be whatever variable is in front of these x, y, z variables. So the first one's going to be, well, x plus y plus z, that's just going to be 1, 1, 1. So n1 n1 is equal to, with the components 1, 1, 1, and then n2 is going to be 1, negative 2, and 3. 1, negative 2, and 3, like that. Alright, so that is what we have. Alright, so if theta is the angle between the planes, we can apply the equation for the geometric interpretation of the dot product and get the following equation. Because yeah, so then basically we need to know the angle between the planes is just the angle between these direction vectors. So let's take a look at this. And if you recall from my earlier video, the geometric interpretation of the dot product is basically we get a cosine theta. Angle between the two vectors is going to be equal to the dot product of two vectors. Divide this by the absolute value or the distance of the lengths of each one. Multiply by each other. Like that. Yes, epic stuff. So this equals 2. So the dot product, this is, yeah, the top part is going to be the dot product. This is going to be 1, 1, 1, the two vectors, dot, 1, negative 2, negative 3. And now this is going to be divided by the lengths. Well, the bottom one, this is going to be length is going to be 1 squared plus 1 squared plus 1 squared. And then multiplied by, this is going to be this one here. 1 squared plus, this is going to be negative 2 squared, as is going to be 2 squared. And then plus 3 squared, like that. So let's see what this gets. This one we know is just going to be 3. This part right here, or the inside, I was just going to look at the inside. So this part right here, that's just going to be 3. This part inside is going to be, well, 1 plus 4 plus 3 squared is 9. So this is going to be 14. So the inside is going to be 14 like that. So put these all together, we get this is going to be equal to, yeah, this equals 2, and then here's the dot product. So this one's going to be 1 times 1. Plus, yeah, so we multiply and add the components. 1, negative 2. This is going to be negative 2. Those erases plus, put a negative 2. And then the next one's 1 times 3, so plus 3. Divide this by square root 3 times by square root 14. Alright, so then what this is becomes, well, 1 plus 3 is 4, the minus 2 is going to be 2. And then this one here is 3. We could put the square roots together. 3 times 14 is going to be, well, 14 times 2 is 28. And then times by another, add another 14. So it's going to be 38, 42. Let's do that in our head. That's going to be 42 like that. So what this means is, this means that cosine theta equals to 2 over square root 42. So then the angle theta, we could use the inverse of it. So inverse, inverse theta. The inverse of this 2, 42 like that. So the inverse of that. Yeah. So this inverse or arc cosine, of this 2 divided by square root 42. If you plug this into the calculator, what we're going to get is, well, this equals to roughly 72 degrees. Just quite epic stuff here. I'm going to box this in. Alright, so that's 72 degrees. And now we could do a calculation check. So we could write a cosine, the same thing as arc cosine or inverse cosine like that. And then 2 divided by square root 42. And this is using my built-in OneNote calculator. So we go equals space and it goes automatically calculates it. So 72.02, etc. So yes, it rounds up to 72 degrees. It rounds down to 72 degrees. Epic stuff. And now let's graph out the planes and double check our work using the GeoGebra 3D graphing calculator as always. So here's the first plane, P1, plane 1, x plus y plus z equals 1. Then P2, x minus 2y plus 3z equals 1. And then what we could do is also calculate the angle directly using GeoGebra. So angle of the planes P1, P2, 72.02. Absolutely remarkable stuff here. And here's the graph of it. So there's the plane, and there's the other plane like that. The green is the plane 2. So this is P2, P1, and there's the angle 72.02, all shown automatically in 3D. Epic stuff here. All right, now let's take a look at solution to B, and this is finding the L that intersects those two. So find symmetric equations for the line of intersection L of these two planes. So what we're asked to find is this line that's intersecting here, like that. That's intersecting these two planes across like that. Epic stuff there. All right, so we first need to find a point on L. For instance, we can find the point where the line intersects the xy plane by setting z equals to 0 in the equations of both planes. Yeah, so when we plug in z equals 0 into the equation of both planes, well, again, we're just kind of guessing that it would be crossing there, because the line theoretically could never cross that xy plane. And yeah, so this is the x, this is the x, this is the y. I mean, the red is the x, there's the y, and there's a z up top here. But looking at the graph here, it looks like, yeah, it should cross it somewhere across. Somewhere across there, it's going to cross the z equals 0 plane there, or the xy plane. But yeah, so you can, again, trial and error, but in this case, it actually does. So, for instance, we can find the point where the line intersects xy plane by setting z equals 0 in the equations of both planes. This gives the equations x plus y equals 1 and x minus 2y equals 1. So if you look at the two planes, so right here, yeah, you just get rid of this this z, this vanishes, so x minus 2y equals 1, and x plus y equals 1. And let's see if we get values for those. And then whose solution is z equals, x equals 1, and y equals 0. And again, you can see that, so we'll have this x plus y. X plus y equals to 1. And then the other one is going to be x minus 2y equals to 1. And again, just double check there. Yeah, so then there's x plus y, then the z goes 0, x minus 2y plus 3z. And the 3z goes 0. So what we have here, yeah, so we have this. We have to use two equations. There's an x and x line up, so we just subtract this whole thing at the bottom and then get a third equation. So that it cancels out. So x minus x is 0. Y minus negative 2y is going to be plus 3y. And then this 1 minus 1 is 0. So we get 3y equals to 0. This means that y is equal to 0. So 3 just divided out goes to 0. Alright, so y is equal to 0, so that's correct. And then the last one, we just plug that inside. So this means now we'll get x plus, that's this part right here, x plus 0 equals 1. So in other words, x equals 1. Yeah, so we have these 2 points, or these 2 values, so now we have the point. It's going to be 1, 0, 0. Alright, yeah, so the point 1, 0, 0 lies on L, since this point satisfies the equations of both planes. Now we observe that since L lies in both planes, yeah, so then it is perpendicular to both of the normal vectors. Yeah, so this means that a vector v parallel to L is given by the cross product, since the cross product gives a perpendicular vector. So for example, if you have these two planes, so you had one plane like this, has a normal vector. Let's call that n. This is let's call it n1 or n2. Actually, if you look at that, that's the green one. That's n2, like this. So that's n2, and then the other one is over here. It's going to be n1, perpendicular to this. So these are perpendicular. It's not perpendicular to this one. It's perpendicular to the plane, like that. And then this one is perpendicular to the green one, etc. So let's ignore those. I'll just erase that. So yeah, so we have those perpendicular. We'll make this a bit less looking like it's perpendicular to it. So this is like that. It's going to look something like, yeah, let's just call it like that. All right. So then the cross product is going to be parallel to this line right here. This is going to be the cross product, like that. So it's going to be parallel. Yeah, it's going to be perpendicular to these two, like that. But also it's going to be parallel to this line L, so that we know the direction of it. So basically, we know the direction, and we have a point on that line L. That means we can write the expression for that, the full line. And yeah, so we could just do the cross product of that. So then the vector v the direction vector of the line L going to equal to the cross product n1 cross n2 vectors. And the cross product gives a perpendicular vector to these vectors that are perpendicular to their respective planes. This equals to, as always, I, j, k. And then the components, so then n1 vector is just going to be 1, 1, 1. 1, 1, 1. And the next one is going to be, let's just go all the way up here. So that's 1, 1, 1. 1, negative 2, 3. So 1, negative 2, and 3. 1, negative 2, and 3. And now we'll do the cross product as always. This is going to be equal to, cross this out, cross this out. 1 times 1 is 3. 1 times 3 is 3. And then minus 1 times negative 2 is negative 2, but we're minusing, becomes plus 2. Like that. This is going to be I. And then subtract is the middle one. Erase this. Erase. Alright, erase that, cross the middle. Now we're going to have a 1 times 3. It's going to be 3. Minus 1 times 1 is 1. J. And then next one's going to be plus the K setup. So erase this. Cross this one. 1 times negative 2 is negative 2. Minus 1 times 1. Like that. And then just solve this out or simplify it. So 3 plus 2 is 5. And then minus 3 minus 1 is 2. Like that. And then this one's going to be plus negative 2 minus 1. That's going to be negative 3. So minus 3. Okay. Like that. And that is what we got. So 5, negative 2, negative 3. And let's circle this. This is going to be our v vector. Alright, and so the symmetric equations of L can be written as, and again we're asked for symmetric equations of the line as opposed to just the vector equation. So here, find symmetric equations for the line of intersection L of these two planes. And again, remember the symmetric equation is just when you have the parameter set that all equal to each other. So x minus x naught over a equals to y minus y naught over b equals to z minus z naught over c, where the where the a, b, c correspond to this vector v, like that. So that means, or I'll continue it further. So where a, b, c equals to v vector equals to this components 5, negative 2, and negative 3. And also, so and the components, the point here, x0, y0, z0, this is just a point on L. If we remember where we solved it for both planes, this was just equals to 1, 0, 0 as per the setup here. As per here. So we solve it here, the points x is 1 and y0 is z0. And so that one lies on the plane, on the point L. Yeah, so we'll put this all together. We get x minus x0 is 1 over a is 5. This equals to y minus 0 is 0 divided by b is negative 2. And then this equals 2 z minus 0 is 0. Z minus 0 is just z. And then divided by c is negative 3. So there's our symmetric equations. Like that. Alright, so then we have the symmetric equations. Let's just graph this out. So let's graph out the line of intersection using, again, the amazing GeoGebra 3D graphing calculator. So there's a link to it, and there's the, I'm just using the same actual link as above, so KTTT, etc. Let's see this. KTTT, FN, and so on. It's the same equation, just added more terms, just to add the line of intersection. So we could solve this. So there's a plane 1, x plus y plus z equals 1. There's the plane 2, x minus 2y plus 3z equals 1. There's the angle 72 degrees. And now what I did was I did a line just using the vector equation. So there's the point line L, and then the vector 5, negative 2, negative 3 from the vector equation. From the, the vector one here from the cross product. And then what happens is, you'll see this is the plane 1. This is plane 1 plane 2, and there's the line right there, exactly on the intersection, which is absolutely amazing. So yes, it's a great way to double check your work.